Hello everyone. Today we will be discussing about applications of photochemistry, and the reactions we will be considering are called multi-component reaction. So it is known as multi-component reactions. And under multi-component reactions, we'll talk about two different kinds of reaction. The first one will be talking about combustion chemistry, and the second one will be a particular example of atmospheric chemistry. Now, for combustion chemistry, we'll be talking about the one particular or very well known combustion reaction, that is hydrogen and oxygen reaction to form water. Now, this reaction is one of the very well studied reaction, and as you know, the stoichiometry of the reaction is something like this: 2H2O. Now, this is the overall reaction, and this reaction is exothermic in the sense that heat is produced in the reaction. And if you remember from your thermodynamics class, that for exothermic reaction the system releases heat. So it's actually negative in that sense. So it is exothermic by 228.7 kilojoule per mole. This per mole is per mole of water, per mole of the product. And but the mixture of this gaseous hydrogen, and as you can see that it is a huge exothermic reaction, but the problem is that the mixture of hydrogen and oxygen, they are very much kinetically inert, and the reason being they need a huge activation barrier for the reaction to proceed. Now, this reaction can be initiated very easily by a spark or just an amount of any kind of spark or a fire can actually initiate this reaction, which actually provides the necessary activation. And then what happens, some radicals are initially generated, and those radicals actually help to proceed this reaction further to produce water. Now, there has been many proposed mechanism for this reaction, and one of the very well accepted mechanism which I am going to write here is basically involves several steps. And the first step, if you remember the radical reactions which we talked about earlier, which was this bromine plus hydrogen to form 2HBr, that reaction we discussed. And that was a particular example of radical reaction where we are talking about the radicals were the bromine radical and the H radical, hydrogen radical. Here also we will be talking about similar radical chemistry, and there we talked about the initiation of the process where actually first the radicals are generated. Here also we will be talking about an initiation process, but this initiation can be through the spark, to photochemistry, through many other activation mechanisms. And then what we are saying is first the hydrogen as well as the oxygen, they produce the radicals which is H radical and O radicals, and the rates at which they produce, we are just simply write it as omega 0. So, this omega 0 is just overall rate. So, in the sense it is not actually rate constant. So, when we talk about say dH dt, if I have a say rate constant something like k, so then we have to write it the equation as 2 into H2. This 2 is coming because actually there are 2 hydrogen atoms are produced, but in this case we will not use this convention. What we are saying that this overall rate is itself omega 0, and this rate is same for hydrogen or oxygen because it is basically the supply of the energy. So, that is the rate of supply of energy that is dissociating these bonds. And then we have actually chain branching. Now, what do you mean by branching? I will come to that. So, we have H plus O2, and then we have OH plus O. Now this reaction we name it as number 2, and then this is basically the rate constant according to the number of the reaction I am writing at K2. And similarly, there is another branch reaction which is O plus H2, where basically the radicals, as you can see, formed are actually reacting with the hydrogen and oxygen, and I can call it as a K3, and we have OH plus H, and then also we have the chain propagation, which we are naming as number 1. So this numbering is according to one of the proposed model, but this is just arbitrary numbering. So you may wonder why I am writing 2 and 3 first and then 1 later. The reason is usually you write the chain propagation step first and then the branching, but for the propagation step you need the OH radical, which is a product of the branching reaction. So this OH radical now reacts with hydrogen to produce that's why I am writing at K1, and again this is very arbitrary, the 1-2 notation, water plus H, and of course you have some termination, so chain termination, and we have 2 reactions. One is basically the H radical, it can just react, it can just collide with the wall to form half H2, and similarly the H radical can be abstracted by oxygen, and a third body, this third body can be the wall or something else, because when H and O2 reacts, you have an exothermic reaction, and for that some heat is released. So there should be some something to absorb that heat, otherwise the bond will not form. Now the interesting thing what you notice here is that we have written the 5 steps. Now if you look carefully at these branching steps, so there are initiation steps and then this branching step, if you look. Now why we call it as a branching, you see that we actually started with 1 radical here. Let me use some other color. So we have actually used only 1 radical here, H, but then we are getting actually 2 radicals, OH and O. So basically 1 radical is producing 2 radicals, or the radicals are branched out. Similarly the oxygen, there is 1 radical and it is now producing 2 radicals, OH and H. So here also it is a branching example. Whereas the propagation is something like you start with 1 radical and that generates another radical, and that radical of course will again the H radical will of course, as we can see in step 2, the H radical will also generate back the OH, and that is how it basically propagates. And then there are termination reactions, but as we have you can see, we have not written any termination reaction for oxygen radical because there are some issues, because you have to also consider the exothermicity and endothermicity of these reactions. So let me give you some values of this reaction, which is endothermic and exothermic. Like for example, we have some values here. So suppose the oxygen, so if you think the branching step number 2, what you see here, the OO bond energy, so that is broken, because you can see here oxygen bond I have to break, and that bond energy, if you take about say 5.1 electron volt, and then you are forming an OH bond energy. So let us just take that value. OH bond energy approximately is 4.4 electron volt. So the step 2 is actually what you are getting is so you are basically you had a oxygen bond which is much more energetic, and then you are actually forming a bond which is less energetic. So basically you have to supply energy. So this reaction is endothermic. So delta H is plus about, it will be, if I take the difference, it will be about 0.7, 4.4 and 0.7 is 5.1, and which is approximately about, you can always convert it to kilojoule per mole. It's about 70 kilojoule per mole endothermic, whereas if I consider about step 3, where actually I broke a HH bond, and HH bond energy is 4.5 electron volt, and the OH which you are forming is 4.4 electron volt. So 4.5 and 4.4, and this will be about plus 0.1 electron volt, the delta H. So in both cases, as you can see, step number 2 and 3, OH radical is formed, so which is approximately equal to 9 kilojoule per mole endothermic. So thus we see that these reactions, this 70 kilojoule per mole at room temperature, it's less probabilistic because it's much lower than KBT, higher than KBT, and then for this reaction is on the order of KBT, and you can actually have it more feasible. So step number 3 will be more feasible, but step 2 we are baking the O2 bond, that rate will be much slower. Now there are all these details which you can actually approximate, and which you can use to make some approximations. Now let us first try to understand what is basically the rate of the reaction, or rate of, say, the change in concentration of the H atom. The rate of change of, say, free radical density. Now the amount of free radical which will be present in this mixture is mostly the H radical, and because H radical actually is the controller of this reaction, as you can see that we have written the termination also for H radicals but not for O radicals, and since H radical is the controller of this reaction, we are writing this, let me use some other color. So we can write this equation as the radical concentration, change in radical concentration, which is equivalent to saying the rate of change of dH dt of hydrogen atom concentration or hydrogen radical concentration. Now first step was the initiation, so that will be, as I said, for that step dH dt was just omega 0, so we'll just write omega 0, and then we have actually the branching steps where this is being consumed, so it will be K2 into H into O. You just follow the kinetic equation, stoichiometric equation, where these are all elementary steps, remember. So that's why just by looking at the equation I can write the rate equation, and then similarly in the third step H atom is formed, so we have taken into account of this step. Now we are taking into account of this, and then H is formed, so it will be a plus sign. We'll have K3 times O times H2, and then what we will have is the fourth step, where actually again we are having the H atom forming, so it will be plus sign K1 OH into H2, and then we are again the termination step means the H will be vanishing, or H is basically being destroyed or consumed in the two termination reactions, so it will have minus sign, so it will have minus K5 into it will be first K4, because that's the fourth step, that K4 into H, and then again another termination reaction which is K5 H into O2 into M. Now what are the other two radical species? Those are oxygen radical species, and as I said the oxygen radical concentration will be much less throughout. So, which means that we can actually approximate, after considering the energetics which we already discussed, right, the OO bond cleavage is and forming the OH bond simultaneously, that reaction rate will be slower because it is highly endothermic, and that will be wherever you get the oxygen atom forming. So, as you can see that this process, as I am saying, this is bond energy is pretty high, and what I am also saying that I can actually ignore the first step also, saying that reaction is mostly controlled by H radical formation. So, I can actually ignore this step, and then because the rate will be much slower. The reason is actually your as you can see, the H radicals are being in the propagation step. Actually, the H radical is the thing that is being formed. So, what we see here is that we can actually ignore the formation of O radical, that step, that we will not ignore, will not consider any omega 0 for this DODT step. And again, this is an approximation after considering the energetics, and then I will have minus K3 O into H2. So, I am considering only these two steps where actually oxygen atom is formed and oxygen atom is consumed. And similarly, I have one more radical, which is the OH radical, which is being formed during the course of the reaction, as you can see here. So, I will have for OH radical, the kinetics will be DOH dt, that will be K2 HO2 plus we will have K3 OH2, because these are the two steps, these two steps, where basically in both steps OH radical formed, but in the first step O radical is formed, second step O radical is consumed. That is why in O radical equation I have a minus sign, but here actually I have a plus sign because it is for OH radical. Plus as you can see, there is also OH radical in the chain propagation step which is being consumed. So, I have to use minus K1 OH. You can have a look at the equation, yeah, minus K1 into OH into H2. Now, what we are saying is as follows. So, we have actually written the kinetic equations, rate equations for three radicals. One is H, one is oxygen, and one is OH radical. Now, the H is the main main component here, and you have multi-radical components here, but what we are saying that this H actually when the reaction proceeds, this H radical keeps on increasing, and what will happen is that this H radical concentration is not actually small, rather OH radical and O radical concentrations are small, and it is kept small throughout the reaction. So, we can actually make steady state approximation for these two radicals, OH radicals and O radicals, but not for H radical, because H radical is the one that we want to solve using the values of O radical and OH radicals, because as you can see we need those values. O radical is here, O radical is here, OH radical is here, and here also, yeah. So, these things we have to replace. Now, if we do that, if we solve that these equations, so what you will get is that this is very straightforward. So, I will get from here the oxygen radical concentration under steady state approximation. That will be, it is pretty simple algebra, and you will find K2 into H into O2 divided by, so this term, and divided by K3 into H2, K3 into H2. And similarly, from this equation, if I want to calculate the OH radical concentration, which is here, so then what I will have is from this equation the OH radical concentration under steady state is nothing but this term, which is K2 into H into O2 plus K3 into O and H2. Now for O, I can use this expression, which is K2HO2 divided by K3 into H2. Let us just write it, K2HO2 divided by K3H2, and then I have H2 also here, so we'll have H2, and then I'll have divided by, so there will be a minus sign here, so this is 0, so there will be no minus sign, so I'll have K1 into H2, K1 into H2. So what do we see here, this K3H2 gets cancelled out. So what will be left with after we do some simplification? You can easily see that K2H and O2, this will be twice of K2HO2. So this is twice of K2HO2 divided by K1 into H2. So you get some compact form for these two. Now we are going to use these values to get the steady state concentration of these, not steady state concentration, what is basically the rate of the radical concentration, which is identical to hydrogen radical concentration. And that we can do, basically we have to write omega 0 minus, so let us follow this thing, it's K1 H into O2, it is not K1, K2 into H into O, and O is here, as we have seen here, the steady state condition, that will be nothing but K2 into H into O2 divided by, we will have K3 into H2, and then the second term is this K3OH2. So there was a plus sign, plus K3O, and instead of O we'll again use the expression for O, and we know that this K3H2, as you can see, will basically cancel with this K3H2. So ultimately we will be left with only the numerator terms. We can directly write it. So it will be K2H into O2, and then you will have minus, it will be plus K1H OHH2, this term, and again as you can see that OH radical has K1H2, so those will cancel. So ultimately we will have plus twice K2HO2, and then, so in this case actually in this way you can actually write all these terms, and you will see that these terms will basically most of the terms you can actually add and subtract, and there will be some cancellation of the terms. So ultimately what we will get that I am writing is basically omega 0 plus twice K2O2, and then we will have minus K4 minus K5. Let me actually write it like this, minus K4 into K5 into O2, sorry, this will be K5 into O2, not K5 into O2, and we'll have times M, because there will be this third body reaction. So we'll give you a handout where we'll show you all the steps. I'm not just for to save time, I'm not going through all these steps. but you can practice it and see whether this final expression is coming, you can derive, and because it's pretty straightforward. And then we'll have H2 here, and so H2, instead of H2 we are just writing H concentration, we are just writing it as N. So this is this term, as you can see, this twice K2 HO2, those terms actually. So instead of H I wrote as N here. Now what we can write about these terms is something like this. So we are almost done, but we will show it in a slightly different way. So I am writing it, look at it carefully, as omega 0 plus f minus g into n, where f is this entire term and g is this entire term. So k4 plus k5 into O2 into m. Now this is just again this is just a notation. Now what will happen? So if I want to solve the equation for n, so what will how it will look like? So as you can see that this n will be omega 0. So this is just a differential equation. So you have to move the dt on the other side, and then you put some initial concentration, but we are saying that at time 0 the n was 0, that way you can solve it. And as you can see that it will be a logarithmic integration, because it's you can see that dx dt is a plus bx kind of thing. So dx dt is a plus b into x. So what we'll do is a plus bx is dt, and then you integrate, and it will be 1 over b ln it will be ln a plus bx. So that will be equal to t after integration, and so the limits were t minus 0, and here also we took it to be so the if I take the limits when let's say it is t, and then evaluated between 0 and some arbitrary time, and here also when x was, we can think x is basically the radical concentration here, dn, n is x. So it was 0 initially, and then at the final time it was x. So when I put this 0, it will be nothing but ln a. So what we'll be having is basically 1 over b. So you can simplify this thing. So it will be 1 over b ln a plus bx minus ln a, and that ln m plus minus ln n, you can actually take it as a ratio, and then whatever you have in the left hand side, you can actually move it on the right hand side, because what is b? B is basically f minus g, that will be multiplied with the t, and then you will get finally an expression something like omega 0 minus divided by g minus f times 1 minus e to the power minus g minus f into t. Let me just do it for you. From this what we will get, so this b I am just multiplying on the right hand side, it will be bt, and suppose I am using an extra minus sign. So what I will have here, just to I introduce the minus sign here, so I will have here ln a by ln a plus bx, and which means actually a divided by a plus bx is nothing but e to the power minus bt, and that you can now easily solve. You can easily see what is a and b. So that way actually you can write this equation. Now you have to be a little bit careful, like so I use the minus sign, or we could have actually skipped the minus sign. So that you write it as 1 over b, or the b thing we can move it on the right hand side. So let us solve this integration. So let us now solve this equation or integrate this equation. And what we are doing here is we can actually think that this integration is nothing but dx dt is a plus bx kind of integration, where a is x is n first of all, where x is n, and b is omega 0 and a is omega 0. Sorry, that's how we have written, and b is simply f minus g. Now so the integration is dx by a plus bx is dt, and then you integrate between the limits 0 and t, and you can approximate the radical concentration at time 0 was 0, at some arbitrary time it is x. So this is a very straightforward integral. So this integral is ln, it will be 1 over b ln a plus bx, that we have to evaluate between the limits 0 and t, and then the right hand side is pretty straightforward, this t. So what we can write, so ln a plus bx at t is it will be basically x here. So that is ln a plus bx, and minus when it is 0 it is ln a. So that you can write it as ln a plus bx divided by a, and that one you can write it as bt, and then I can actually rearrange it like it is. I can write it as 1 plus b by a into x is e to the power bt, and then I can solve it easily for x, and what I will get is x is nothing but it will be if I take the minus sign, so I'll have minus 1 plus e to the power bt, and I'll have here is a plus bx, so I have written, and then I'll have here a by b. So that way you can actually rearrange all these terms, and then what you will figure out is the solution here will be n is nothing but omega 0 divided by so my b was f minus g. I'm just writing here as g minus f, and if I do that, then actually I will introduce one minus sign, and that minus sign gets cancelled with this minus sign. So I'll have plus 1 here, and also I'll have a minus sign here, and instead of b writing as f minus g, I'm writing it as g minus f. So I'll just write it as g minus f into t. So that will be the final form of this final solution of this differential equation. So then this will be true if actually g is greater than f. Now when g is greater than f, we can actually figure this out. What is g? G is this term k4 plus k5 plus into O2 into m, and f is twice k2 into O2. So this means actually g has the termination step. If the termination, if it is actually terminating first, that rate is first, then actually g will be greater than f. But if it is the other way, so I have say g is basically more than or g is basically less than f, we can actually write it in the original form, like in the sense that not introducing the minus sign. So in that case f minus g is positive, and I'll have minus 1, but that I can write it later. So I can write it e to the power f minus g e to the power f minus g, which is a positive quantity, into t and minus 1. So that is the usual way people would write the solution. So I have basically two conditions. One, this g is greater than f means actually again the termination dominates, and then here the G is actually less than F, means actually you have the other condition, which means actually your H atom concentration, because if you see here what is G and F, you have actually 2 K2 into O2. So this is basically the rate of these processes. So if you figure it out from here, so this 2K2 plus O2, these are basically the branching processes correspond to. So if that rate is more, so we can actually say that it is more branching, because this 3-body term is only coming from termination, and this is coming from mostly from the branching. So we'll have basically competition between whether it is terminating or whether it is branching. Also, which is important to note here, it will also depend on the pressure of the oxygen also. So we'll come to that later. Overall pressure of the gas. So there can be actually other equations which we have not considered, because this is a very complex process, this kinetics. Now let us just try to draw or plot what behavior we are going to expect for, say, N versus T. So let's say if I actually plot this thing, and I am also saying that I have actually normalized it, or we do not need to normalize, like the final value will be omega 0 into G minus F if I am plotting the first curve, where actually G is much greater than F, G minus F. Suppose this is the limiting thing, and then what you have, it is 1 minus e to the power minus a positive number into T, so which means actually it will have growth. So for long time, what we are seeing here is actually it is kind of saturating. Now when it is happening, because actually you are having the reaction, but with the longer time what you have is the chain is basically terminating. So because the G term is more than the F term, and the G term actually includes the termination step. On the other hand, if we have the other condition, so this will be the true for G is greater than F. If G is less than F, then you have actually what you can see here, we have actually a plot which is omega 0 into F minus G, that factor, but this part will actually emulate any other term, because this is a positive part and this is e to the power positive number into T. So that then actually will have a very high buildup of the radical concentration, which actually corresponds to explosion. So as you can see that if you do not have any control over the this radical branching or the propagation steps, which is basically dominated by H radical formation, and then actually it will be an uncontrolled reaction, and then you will have an explosion. Otherwise, if you can actually quench the reaction, in the sense that you make sure that these radicals actually have a termination path, which is just because of collision or because of abstraction of this hydrogen radical by the oxygen molecule, which is this reaction, this O2H kind of species. This species is, by the way, spectroscopically identified in oxyhydrogen flame, and that's why people proposed this particular pathway. And then actually you can actually explain under what condition you will have the termination dominating, under what condition actually you will not have actually radical radical production or branching dominating. In those cases it will be uncontrolled or explosion. Now there will be also other pathways which is much more difficult to analyze, in the sense that you can actually have this HO2 species, which is very interesting, which I said that this is spectroscopically has been identified in the oxyhydrogen flame. That also has its own interesting dynamics in the flame, and then it is very much pressure dependent, that I am going to discuss briefly. and then actually this species itself interferes, and it actually can produce H2O2 and many other species, and then this H plus HO2, as you can see, I am just writing the equation once again because there are multiple species formation. We can have OH radicals also again generating from this HO2 species, and then we can have H2 plus O2, sometimes we can have H2O plus O radical back, and then there are many other events like H2O2 plus M. Again, M is the third body, it's in this case it's a second body, it can be something else, anything else, like it can be oxygen itself, it can be the wall, it can be the hydrogen itself, and you have a very interesting chain of reactions which all will participate if we have an enhanced amount of this HO2, because these are all HO2 initiated reaction, because that is producing H2O2, and then H2O2 has its own interesting photochemistry. In this case, it's not photochemistry, it's basically the radical chemistry which is initiated photochemically or by spark, and we'll have O2 plus H2, H plus H2O2, it will be O2 plus H2 plus H, this will be OH2, or HO2 back you can get, and then similarly you can have many other reactions like H2O plus HO2, and you can have also the three body reactions like H plus OH plus M, which is H2O plus M, and then again H plus M, you can have H2 plus M. Now you can see the complexity of this entire hydrogen plus oxygen water reaction. There are enormous number of side reactions or the small elementary reactions that can happen, and in order to explain the overall thing, you have to study each of these reactions, think about their thermodynamics, how much they are endothermic, how much they are exothermic, how much they are contributing. All these things will come into picture. Now, what finally we are going to conclude this section with is basically what happens in reality. So, if I suppose plot the rate, which is the dN dt thing, after solving all these things, you cannot of course solve it analytically, you have to do numerical solution. So, in very early stage, when you have actually the propagation is or the branching is controlling, so you have a zone where actually you have an explosion. So, this is we call it as a zone 1. So, here actually the x-axis I am plotting as a function of say pressure. So, if I increase the pressure, so I can have a explosion in the very early pressure range, but then so it's basically initially it will be a slow reaction, but eventually there will be a explosion, and here actually it's a slow reaction in the sense. So, this curve is actually combination of these two curves which we have drawn. Like I had I'll have a termination, if termination dominates I'll have an kind of explosion. So, what I am saying is that overall I'll have a growth something like that. So, in that very slow reaction means actually you have very low pressure, and then chances of getting heated, chances of getting being deactivated after colliding with a wall is basically much less, and then you have an explosion zone, and this is called explosion 1 zone. And then interestingly, if you keep on increasing the pressure, sometimes what you will have here is that you will have a very interesting quenching reaction, because now the H atoms will be further abstracted, because as you can see these H atoms, if you increase the pressure, you can actually generate this HO2 kind of species, and then this HO2 now can actually abstract this interesting species HO2 can now abstract the H atoms, and then what you will see is that you will see a drop in the reaction rate, and so you have a region 3 where actually you will see things are burning. It's called atmospheric flame. So at a higher pressure you may see burning, but if you keep the pressure at a very high, so what will happen, the exothermicity of the reaction will actually control will actually lead to explosion again. So that's why I will call it as a explosion 2 region, where due to the very high pressure all these reactions are happening and a lot of heat will produce, that causes the explosion. So this explosion 1 is due to uncontrolled rate of the reaction, and this explosion 2 is basically the heat generated because of the reaction. And then in between you will have a drop in the reaction where you will see things are burning, but it's not actually exploding because you have some kind of like decreased the reaction rate and made it actually in kind of flat. It's also kind of a steady state kind of situation. It is indeed a steady state, but it's not a same steady state as we discussed, like it's not a very low concentration steady state. Now this thing was actually observed, and what happened is that in 1937 we just put it in the note. I'll show you an interesting picture where it was shown that there were two accidents happen. In one case there was an space hydrogen filled shuttle, and its name was Hindenburg, and that Hindenburg actually exploded, but then the photographic images showed that actually it did not explode, it actually did burn. So Hindenburg explosion, you can actually Google it, and then you will find that this was not exactly explosion, this was actually burning. So why this burning happened? Because it was lying at some pressure zone like here, and at that elevated pressure you do not explode, but actually you burn. And then for another example was the explosion of the space shuttle Challenger explosion. There also people showed the photographic image showed actually this is a true explosion because it showed that it is kind of exploding, but then the question was why it is exploding. They had a very controlled reaction so that this explosion doesn't happen. Then they figured out that when they made this spacecraft Challenger, so what happened is that there was a faulty O-ring, and this which actually is at a pressure gauge, and that faulty O-ring actually leaked, and it was faulty, and that's why a lot of gas actually leaked through it, through the window. And then what happened, it caused actually a huge change in the pressure, and for that it actually fell in the very high pressure region, which actually caused the thermal expression to happen. So this is kind of a thermal explosion where you have lot of heat is being released, and that is your explosion. It has nothing to do with the uncontrolled radical reaction. It is more like a heat generated suddenly. So there are interesting examples, real life examples of this hydrogen oxygen combustion reaction, because this is used as a rocket fuel. There are many other important combustion reaction. One of them is actually this combustion of methane and other hydrocarbons like acetylene, which we actually are also used like whenever you use say cooking gas, so it mixes with oxygen and then it burns. So what is the chemistry for that? So these are also radical chemistry, and these are all, there are also branching and other things involved, and it is extremely important that you have to control the pressure, because if it is not controlled, then actually you might have an explosion. There has been incidents, of course, you are aware of that gas cylinder explosion. So you have to be very careful in controlling the pressure and other things, so that the combustion is kind of controlled and you have a very good flame, which is a burning flame, but not an explosion, because so that you can cook your food. So there are many practical examples, but again we are not go into the details. So in this lecture, to summarize, we have given you a flavor that what is most important part of this thing is that that under two conditions, like you can have the radicals, if the termination happens, it will be the reaction rate actually will be quenched eventually. That will happen at an extremely low pressure, because you can think that molecules are not colliding with each other, but there is a fairly good chance that it just hits at the wall of the container. But if it is a moderately high pressure, then actually there will be a lot of collision and lot of radical production, which might lead to uncontrolled reaction, which is explosion. But then again, if you have too much pressure, then you have an interesting chemistry for this HO2 species, which can actually quench further the reaction. But again, in a very high pressure limit, you can have a thermal explosion, because everything is I mean, overall the reactions are exothermic, and then you have an explosion for explosion happening, which is the thermal explosion zone. So we'll just stop our discussion on this radical, the first part of the radical chemistry, which is the combustion chemistry here. So in the next lecture, we'll be talking about the atmospheric chemistry, but there also we'll be talking about similar things. So in this lecture, we basically covered the first part of multi-component reaction, and which is the combustion reaction. And again, we just gave you one example of the combustion reaction, which is hydrogen and oxygen combustion reaction. Thank you.